So I'm David Hopper. I'm a PhD student in the physics department, but I do the research here in the electrical systems and engineering department through the physics graduate group. And so today my talk is titled The High-Fidelity Readout of a Room Temperature Solid-State Qubit. And this work was performed in the Quantum Engineering Laboratory, which is down in the basement of town. Feel free to drop by and say hi sometime. So to start this off, I want to sort of set the background for what we're going to be talking about. And the field we're going to be focusing on is something called quantum information science. And really what this is asking is, how do we mathematically understand information theory when we assume that the matter storing this information is quantum in nature, i.e. it obeys quantum mechanics? And there are a few different things we have to take into account. The first of that is the superposition principle applies to matter. And I'm going to describe this in terms of information theory, where in the classical world we have a digital bit, which is discrete. You're either 0 or 1, and that's how most computers nowadays work. But you could also come up with an analog bit, something that's continuous. You could take a voltage from 0 to 1. And now a quantum bit, or a qubit, kind of takes both of these aspects. It's both continuous and discrete. And now what I mean by that is, whenever you measure your qubit, you will either get a 0 or a 1, so your results are discrete. But you have this continuous probability that you can 50% of the time get 0 or 50% of the time get 1. And this probability is actually what obeys the superposition. This probability comes from a differential equation that produces wave equations. So that's where the superposition principle stems from. And now, one thing I mentioned there is that you have to measure your qubit. And that's something else that's fundamentally different. And so what we typically say, measurement is when a classical observer is interfering with the system being studied. And what that does is it'll take your probability distribution and project you into one of the answers. So if originally you're half in 0, half in 1, when you measure it, you will always be in what you get. So these are kind of the what is different and what you have to take into account. And there are a lot of different scenarios you have to be careful with, and there's a different tool set you use. But to motivate this a little bit further, I want to talk about some of the applications, and they really come down to three things: computation, communication, and sensing. So the first one I'll talk about is probably the most famous, and that's the computational aspect. We're all familiar with factoring primes. Just as an example, you can use the number field sieve, and for, say, the number 21, it's pretty easy. You do this in elementary school. It factors into 3 and 7. But now, what if I gave you this number? It's a little bit challenging. Sort of where do you start, and how would you do that? And how many primes does it have? Is it 2, 3? It's a difficult problem. And in fact, this is a RSA 768 number. It was posted on their website as being sort of a, if you can crack this problem, you can, basically RSA 768 encryption is null. And a group of researchers in 2009 did it. It took them 2 years. These are the results if you're interested. But the reason this is so hard is that this algorithm scales exponentially with an increasing bit size. And this is sort of the root as to why our encryption schemes work. Usually RSA or any public encryption scheme shares a very large prime number, and only the parties who are involved know the factors. And so someone looking in has a very difficult time sort of backing it out. But now, when you go into quantum information theory, there's actually an interesting result called Shor's algorithm. And it's a way of getting a better or a faster way of factoring primes. And the way you do that is you're given some number n, and you convert this factoring problem to a period finding problem, where essentially you pick a random number less than a, you start calculating the modulo function a of n, and try to find how many times you need to repeat that process to kind of loop around. And now, in quantum information processing, there's a very, very good algorithm for finding the period. It's called the quantum Fourier transform. It's very efficient. And so basically any problem you can convert to the factoring problem, you can then solve efficiently. And so this only scales polynomially in complexity. So for very large numbers, you'll start getting exponential speedups in the computation time. Now, you don't have to worry. The current record is factoring 21. This is actually, while the computational complexity is easy, the implementation is difficult. So we're not quite at the level of cracking all RSA encryption, but we are getting there. Another result is that we can actually resecure our communication lines using the same principles. And it really comes down to something called the eavesdropper problem. Well, let's say Alice and Bob want to open up a communication link and share information that they know only they will understand. Now, typically, you come up with some public encryption scheme, but an observer can tap the line and read off the information coming through. Now, if you can crack the encryption scheme, Alice and Bob will never be aware of that, and so you can never tell if someone is tapping your wire, essentially. Actually, the NSA has flagged this as a primary research goal, where they, one, want to figure out how to break classical encryption, and they have identified a quantum computer would be able to use it. But at the same time, they're also looking into ways of securing their own information. And we do that through something called quantum key distribution. And the idea of it is that Alice and Bob, again, want to share information. And instead of opening one link, they open two, a classical link and a quantum link. And now, as I recalled in the second slide, that the measurement in quantum mechanics does matter. They will share information over a quantum link, measure the results, and compare it. And then if Eve wants to tap the wire, Alice and Bob will know that someone is listening in on their wire. They can abort their communication, resecure their line, and try again. Now, this is a very case-specific thing. You really want to secure high-value information with this. And that really applies to governments, banks, large companies that are kind of moving money around. But this is actually kind of taken from academia, and it's been implemented by industry already. You can go to Toshiba, and you can buy a commercial quantum key distribution system. It's a secure data rate of 300 kilobits per second, and it's within a city. So it's a little limited, but it is out there, and people are working on improving the capabilities of this. And now for something a little bit different, developing accurate sensors, which this may seem a little different from what I have been talking about. But you can use these fundamental building blocks to really accurately sense the environment. In the previous two applications, you were trying to eliminate these qubits from the environment. But here, we use that to our advantage. And so one of the classical examples of this is actually nuclear magnetic resonance imaging, or MRI. And usually, you have some bulk ensemble. It could be a bunch of proteins, chemicals, a human body. It's an MRI machine, the same principles. You put it in a big apparatus with a big magnetic field, and you can gain information about it. But one of the interesting things from quantum information science is that you can start scaling this down in size. And what we have here is a picture of a hard disk bit, or bit structure, that was imaged using a qubit that they were able to scan around on top of it. And so what you're seeing here are actually the memory bits written into the hard disk that you can then image. So this example has about 100 nanometers of localization. You can do better than this. And there are a lot of applications in condensed matter physics, biology, biochemistry, where you can start putting sensors in very specific locations and get more information. And so you're not limited to only magnetic information. You can get temperature, you can get electric fields, and you can get chemistry if you are careful. But another one that's interesting is mechanical sensing. So like I said, matter obeys quantum mechanics, and it exhibits wave phenomena, so you can develop very accurate mechanical sensors. And there's a funny viewpoint from the American Physical Society where a very small trampoline of silicon nitride was able to sense very small forces. And they're able to detect 16 attonewtons of force in 1 second. If you're not familiar with that unit, that's equivalent to two people standing 100 kilometers apart, and the gravitational force between them. So very, very sensitive, and pretty quickly, too. 1 second isn't too long. So now, I mentioned that these are maybe they seem different on the front. But if you sort of look at the fundamentals of how you implement these things, we usually write them down in something called a quantum circuit diagram. And what it looks like for prime factorization is this, where you have your input qubit states and you act operations on them, perform the quantum Fourier transform, and then you measure them. For sensing, you have 2 qubits here, and you act operations on 1. And then quantum key distribution, you take an entangled state, which is sort of a generalization of a superposition, and then you send it to Alice and Bob. They measure it, compare the results, and then they can determine if someone was listening or not. Now, one thing I want to highlight is that all of these diagrams have this little measurement block. And this measurement block is taking a quantum state and converting it to classical information. So that's something we can measure in the lab. But in these circuit diagrams, they really take this for granted. This is a challenging task. And to kind of flush it out a little bit more, we have our qubit states. Sometimes I'll refer to them as eigenstates. And what you need to do is map these states to observables. And what I mean by that is we need to somehow take this quantum state and get it to produce something we can measure in the lab. For us, we're really good at measuring electrons and photons. So we need to have a physical system that can produce that. Secondly, we need to detect these results. We're getting very good at this. The electronics are not really limiting us anymore. But then we need to somehow convert this quasi-continuous probability distribution to a discrete value of 0 and 1. And I say quasi-continuous because these are, whenever you detect electrons and photons, you're counting an integer number of them. So Poisson statistics is always dominating. Now, I'd like to emphasize that all of these points are platform dependent, especially this one. There's a lot of physics and understanding of the system in order to get this step, as well as these steps as well. Different fields have different conventions, and it's a little messy at this point. And to add on top of that, you have sources of error in each of these points. And if you're not careful, that error can dominate your signal, and then essentially this whole process becomes worse, and you have to repeat your measurements to overcome that noise. Now, for this talk, I will focus on one specific platform and kind of walk us through how do you go from identifying your eigenstates to getting out the 0 and 1. And our platform of choice is Diamond. I mentioned this is a solid-state qubit, so we're going to be looking at something inside of Diamond. And part of the reason it's nice is that it has a large electronic band gap, 5.5 eV, high thermal conductivity, and the most common isotope of carbon is 12 carbon, which has 0 nuclear spin. So our qubit is going to be a single spin. You can imagine if you have other spins in your solid, it's going to introduce unwanted noise. And now, similar to silicon, where you can dope it and you can get N-type conduction, P-type conduction, you can also dope diamond, but you don't get as clean of conduction. But what you get are different colors of diamond. And so instead of being electrically active, you have optical active defects. So whenever you see different colored diamonds, these are actually different materials in the diamond. For example, this yellow and brown is a lot of nitrogen, blue is boron, and this dark red and pink is something called a nitrogen vacancy center, which is probably the most studied defect in diamond because it has interesting quantum properties. Recently, it's been able to implement a loophole-free Bellows inequality violation. This was about a year ago very popular. It was in the New York Times. And essentially what these researchers did is they took 2 electron spins in diamonds separated by a kilometer, entangled them, and were able to prove that they were entangled and that quantum mechanics was governing these systems. But also, more recently, people were able to resolve a single protein using a nitrogen vacancy center, which they've kind of taken the NMR from bulk, kind of Avogadro's number of material down to the single protein level, which is essentially, you can't do better than that. But this is an interesting platform because you can do these computational aspects as well as the sensing aspects. So you can really do everything that kind of quantum information is promising. Now, I mentioned that we're going to be focusing on the nitrogen vacancy center in diamond, and to be a little more specific, it's a substitutional nitrogen atom situated next to a carbon vacancy. And the dangling bonds in the lattice basically set up what looks like a fluorescent molecule in free space. So you have electronic states that you can access optically. And it also has a spin state. It's spin 1. And what that means is there are 3 spin sublevels that you can access. You have ms equals 0 and plus or minus 1. And so the way we interact with this is through visible light. And what we do is shine 532 light on. And then when the system relaxes to its ground state, the 0 state is going to produce red light. And the plus or minus 1 state is going to go through a non-radiative decay, i.e. it's not going to produce as much light as the 0 state. And a nice result of this is that actually you can initialize the system into 0. If you turn this green light on long enough, the system will end up in the 0 state. So we can initialize our qubit, and we can read it out, which are 2 sort of critical requirements to be able to do interesting stuff. And so we usually like to say the ms equals 0 state is the bright state, and the plus or minus 1 is the dark state. And so you can actually do some pretty basic implementations of quantum mechanics. If you've ever taken perturbation theory in quantum mechanics, you do Rabi oscillations. And this is actually data from our lab where we're performing a Rabi oscillation, which is showing that we can coherently control this ground state. So we can go from 0 to plus or minus 1 and back. Now, there are imperfections with this. Diamond has a very large index of reflection, 2.4. And what that means is you get total internal reflection. So these emitters are in the diamond, and so when they emit light, some of the light will get reflected back in, and we never detect that. So that reduces our signal. Furthermore, this optical spin pumping reduces the contrast between the spin states after 500 nanoseconds. So that means we can only measure the qubit for 500 nanoseconds. And there are other charge transitions that occur. This green light can actually eject an electron from the NV center and convert it to a neutral charge state. So all of these sort of combine that when we perform a single measurement, for the dark state, we measure 0.03 photons, and for the bright state, 0.05 photons. So in order to get something like a signal-to-noise ratio of 10, which is usually a pretty good benchmark, you have to repeat your experiment 40,000 times. And this becomes very challenging when what you're doing takes a long time. And now, to bring back this image of the hard disk drive, this was actually imaged with an NV center. And so we just do a few calculations. We assume it's the 5-micron scan, and each pixel is 50 nanometers, so you have to serially acquire each point. This would take 33 minutes to acquire. And I don't know how good their stages were, but trying to keep anything still to 50 nanometers for 33 minutes is challenging. You don't want to be limited by that. And now for the computational aspects, you need to do something called entanglement verification. And the way we typically quantify multiple qubits is we write down the density matrix, which grows in size as 2 to the number of qubits. And so you have to measure each of these points in order to verify that you've generated entanglement and your protocol is doing what it should be doing. But in the Henson paper that I mentioned, they were generating entangled events once every hour. And the only way they're able to do that is they had a high-fidelity readout, but this was at low temperature. And to be honest, you don't want to have a $100,000 cryostat for every qubit you want to use. But this is infeasible at room temperature, because if you think once every hour, and you have to repeat that 40,000 times, it's too long. Not going to be able to do it. So we need a high-fidelity readout at room temperature to start, 1, implementing more of these advanced entanglement protocols, and increasing the throughput of our magnetometers. And now, to kind of come back here, now for our NV measurement, we know what we're going to detect. It's going to be photons. This is an optically active qubit. We should stick with what we know. And we can detect these with very good single photon counters. But now we need to focus on sort of getting our qubit states mapped to an observable. And I'm going to go back to something I said that was actually a problem, and it's the charge structure. So the negative charge state, which is the one that has all the nice properties, has a zero photon line of 637. That's the longest wavelength we can excite the center with. But there's also the neutral charge state, which has a blue shifted zero photon line. And the nice thing about this structure is that we can choose a wavelength in between 637 and 575. And if we detect photons, we know it had to come from NV-. So this is a way of determining the charge state reliably, and we can actually do it very well. So this is data taken from our lab where we shine orange light and we measure photons for 3 milliseconds. And what you see are two Poisson distributions. You have one here and one there. And what that's signifying is that if you're in NV neutral, you don't produce many photons, and so you're coming from this distribution. And if you are in NV-, you're producing many photons, and you come from this distribution. And what we can do with this is develop a single-shot readout. Basically, we impose a threshold condition by this red line, and if you detect more photons than 2 photons, you say you're in NV-, and if you detect less, you say you're in NV neutral. So this is our example of a quasi-continuous to discrete conversion. In quantum information, it's always this sort of thresholding strategy. And I'll refer to single-shot readout many times in this talk, and that's what I mean. You pick a threshold, and you say, I was in NV- or NV neutral. And another nice aspect of this, you can probe the charge non-destructively. That means you can measure it, and let's say you get NV-. When you look again, you will still be in NV-. So now we have a high-fidelity measurable, but all I've written here are the charge states. There's no information about the spin state. So we need a way to sort of map the spin state onto the charge, which we can then read out very well. And there are some interesting results coming from people who were shining both visible and near-infrared light on NV centers. Basically, what this is showing is you can modulate the emitted photons just by turning on infrared light. And there's also some weird charge dynamics that people were reporting. No one really explored these too well. It wasn't hurting their experiments too bad, so they just went forwards with it. But we sort of hypothesized that maybe there's more complex structure to what was going on here. And we noticed that the singlet band, which is sort of that non-radiative decay pathway, can actually absorb near-infrared light. And so we're kind of saying that this is all stemming from this fact. And the nice thing about the singlet is that this is where the ms equals plus or minus 1 state decays into. And we can populate that state very well if we know the initial spin state. So we wanted to set out and try to discover this. And so we have our plan, convert the spin state to a charge, and then measure that charge optically. But this is only in theory. We need to measure this somehow. And in order to do that, we need to build a microscope that's able to image these spins, and we need many colors to do that. I've mentioned 532, 592, as well as a near-infrared source. So we need 3 colors going into a microscope that then allows us to detect photons coming out. Now what that looks like is this, where we have our microscope here, which is looking at our diamond piece, and we look at bulk pieces of diamond. And on them, we make these solid immersion lenses, which gets us around the total internal reflection. Basically, any light that incidents the diamond surface will be perpendicular. And then we have a little bit of timing to take care of. The optical dynamics that kind of go from the triplet to singlet occurs on the 10 nanosecond timescale, but these charge dynamics occur on the millisecond timescale. So there's many orders of magnitude difference in the timing we need to take care of. And the way we do that is have an arbitrary waveform generator that sort of does all of our fast timing, and then a data acquisition card that's providing the clock and taking care of the longer sort of kilohertz rates. Now, just diagnostic measurement, how much light we're getting out of this. We're doing pretty well. We're getting about a 6-fold increase over just a planar surface. And more importantly, we're getting more power into our diamond. So now, the first thing is we wanted to recreate sort of the quenching measurements that people had measured, and that's the drop in photoluminescence. And what we've done here is just measured photoluminescence with just green and green plus infrared. And so as we increase the near-infrared power, we see what is quenching, i.e. the photoluminescence has dropped. But we also see this strange increase in the photoluminescence, which people had not observed up until this point. But we can very easily measure the charge distributions that are producing this. And what's interesting is that if you measure the amount of NV- population, it directly tracks the photoluminescence. So we can say that this observed PL quenching is due to NV- ionization, i.e. we're removing an electron more efficiently with near-infrared power, and that there's some non-monotonic charge dynamics. Basically, what I mean by that is you increase NV- population, and then you decrease it. And what that means is that you have competing processes that are occurring at different powers of near-infrared. Also a nice bonus out of this is that we found a way to initialize into NV- better than you used to be able to do. So usually when you shine green light, you get NV- 75% of the time. But now we can get up to greater than 90%. So that helps with our initialization fidelity. So we wanted to sort of probe this a little bit further. And so we developed a multiphoton absorption model. And so what I've displayed here are basically all of the allowed transitions for going from NV- to NV neutral, which is ionization, or back the other way, which is recombination. And these lines are just signifying that if one line is one absorption of that color. So this transition is absorbing 2 green photons. This is absorbing 1 green, 1 near-infrared. And what we can do with this is sort of boil it down to a 2-state model and then solve the steady-state solution to these in terms of all of the powers. And we can get a nice equation out of that for the NV- population, and it fits very well to our data. And what that says is that this model is capturing the dynamics of what we're observing. But what I'd like to focus on now is sort of this equation, which was our hypothesis that we're populating the singlet and ionizing it. So we can go out and measure that. And the way we do that is we first initialize our system, which puts us into ms equals 0. We can then perform spin control, where we either go into 0 or -1. And then we excite the system for some time. And eventually, we'll separate out the spin states. So the -1 state will want to go into the singlet. And the ms equals 0 will stay in the triplet. Then we come in with an intense near-infrared pulse, and anything that was in the singlet will end up in NV neutral. And then we can probe the charge state. So we should see a spin contrast in our resulting charge measurements. And when we do the experiment, that's exactly what we see. The ms equals -1 has a smaller NV- population. So it seems like our hunch was correct. But we can do a diagnostic check just to confirm that this was correct. This singlet state is metastable, which means it'll slowly decay down to the ground state. And so if we wait before ionizing, we should see the ionized population decrease. And again, it's exactly what we see. We get a nice exponential fit of the NV- population sort of increasing. And this lifetime comes out to what we expect for the singlet at room temperature. And so this kind of puts the final quenching question to rest, that it is singlet population. But we also have a new spin-to-charge conversion protocol. But if you look at this curve, it's not great. We can actually improve it significantly. And the way we do that is through a protocol where we initialize the system, check that it's in NV-, and then we'll repeat our spin-to-charge conversion process so that we excite once, and then any population that ends up in the singlet, we ionize away. So again, this is a similar plot, but instead of sort of increasing the duration of the shelf pulse, we're now increasing the number of times we repeat. And you see that our spin contrast gets much larger, and we still retain the spin, the charge conversion. And we can develop a model for this where we have a lot of different processes, but they're all in the steady state. So we kind of have a transfer matrix that takes us through the system. But what this allows us is to fit our data and kind of pull out some of the key parameters and also quantify it. So we know that we're ionizing the singlet 30% of the time, which isn't great, but it's nice that we are getting a contrast. And our fidelity of the spin state readout is 62%. what that means is that with this non-optimal ionization pulse, every time we measure our qubit, we're confident in it with 62% confidence, which is pretty good. Now, if we turn our yeah.
I don't know what level of fidelity can you hope to shoot for. What is an acceptable level of fidelity?
Yeah, so right around 75% is when people start to say that's good enough. If your fidelity is lower than that, it means you just have to repeat your measurement a few times. Over 75% is kind of where you want to be. And if we can increase our ionization probability, which is just increasing the near-infrared power, we'll actually get greater than 75% fidelity. And then we're in that regime of high fidelity. And this is really just an experimental equipment limitation. And actually, this greater than 75%, by the time you increase your ionization probability, there are other things holding you back, such as how well can you initialize. These sort of flaws all start coming together and getting amplified. But this is the roadmap to getting high fidelity single shot electron readout at room temperature. So we now have confirmed what we set out to. We have our map, the states to an observable. We know we're going to detect. And now we have this quasi-continuous to discrete conversion. And actually, to follow up with your question, when you have a lower fidelity, you want to repeat your measurements to overcome noise. And you actually have some freedom as to how you want to go about doing that. So now, to focus on that, I have just a little cartoon of what the photon distribution for each measurement would look like. You have some distribution of photons from NB neutral in blue and some from NB minus in red. And now there are two ways you could go about trying to process this data. The first one is thresholding, which is convert to a discrete result each measurement. And what that means is if you detect more than the threshold, this black line, you say I was in NB minus, and you assign that as a 1. If you detect less, you say you're in NB neutral, and you assign a 0. And so what your sort of ticker tape coming out of your qubit reader would be 0, 1, 0, 1. And so these are your results you're trying to analyze. But you could not threshold and sum all of your results to the n, and that's sort of a analog measurement where your ticker tape is now just 0, 1, 10, and you're just looking at the total number of photons that come out after n measurements. And now there's a slight complication in trying to analyze these choices because you don't have a single random process producing these observables. You have two. We have our spin-to-charge conversion process, which is not perfect. There's some probability that it succeeds. And then you have your readout. So again, just to bring that up, we have thresholding, where you have to write down a joint probability distribution of a binomial, which is your spin-to-charge conversion, and your readout, which is did you successfully identify NB minus. If you want to go with the analog version, you now have a binomial process for spin-to-charge conversion and a Poisson distribution. And so we can analytically write these down and then start calculating the means, the variances, and so we can get measures of the signals and our noise. And so we define a single-shot SNR, which is a measure of how good is our single measurement doing. And now when we look at how does thresholding compare to analog, we see that thresholding starts to win out. And what I'm plotting here is really just a measure of how many photons you're collecting in each measurement. And we see that right about where you start detecting one photon, which is this black line, thresholding starts doing much better. And this is sort of curious. We're still working on it. And it's sort of suggesting that there is room to be gained by how you post-process your data. And what I have here is just what is the optimum threshold number to pick. Just exhibiting that it is behaving as we want. So now, just to sort of conclude and wrap up, hopefully I've laid out this roadmap of how you take your eigenstates from your system and get out classical zeros and ones. And these sort of rules apply to any qubit, and we now have a way of doing it for the NB center at room temperature. So we sort of resolved the quenching issue in the field using multiphoton absorption. Nicely out of that, we got an all-optical NV- initialization protocol. And we have this experiment-independent framework for measuring room temperature diamond spins. What I mean by experiment-independent is we now have a formalism for doing thresholding, which applies to single NVs with very nice behaved charge dynamics, as well as many NVs where you can't threshold. You can use the analog measurement to still get increases in your SNR. And now moving forwards, there's some further investigations to look at the spin polarization of the NV- protocol. So kind of ask the question, what is our total initialization? How well are we doing in that sense? Look for maybe some spin purification that could help us with this first part using our spin to charge conversion procedure. And finally, investigate this readout protocol in other diamonds. You can look in nanodiamonds, where instead of a big 1 by 1 millimeter piece of diamond, you're looking at a 40 nanometer piece of diamond. And bulk ensembles, where instead of one NV, you have hundreds of NVs. So with that, I'd like to thank everyone who helped with that, Dr. Richard Grote, Dr. Anne Marie Exarchos, and Professor Lee Bassett, and the whole quantum engineering lab here at Penn. So thanks.
Like you said, the fact that the analog is less good than the discrete is very odd.
So kind of the sort of this procedure where you're repeating.
Which is this part, and then the quasi-continuous discrete.
So we're using this repeated procedure to sort of map onto the observable that's going to produce our quasi-continuous distribution. And so what we found is that if we can tune these parameters precisely, we can do better than just trying to go for a single shot. And so really, this is just trying to increase that probability of successfully converting to NV-. And so what that does, and maybe this is winning your question, is it increases that first binomial, or it increases the probability of that binomial variable, which decreases the noise. So that does come into these analytical expressions where you now have a binomial and a binomial, which seems to have smaller noise than a binomial and a Poisson. So it is interesting.